everybody. Thank you for coming to our talk. We're going to talk about Hadoop, and we're going to talk about Yarn. What you will learn in this talk, if you don't know already, let me do a poll. How many of you know Hadoop? Okay. How many of you know Yarn? 2, 3. How many of you know Java? If you don't raise your hand, you're in the wrong conference. Okay, so most of you don't know Yarn, and that's not a surprise because it's a fairly new thing. So in this talk, you're going to learn about Hadoop if you don't know it yet. You're going to learn what other things you can do in a Hadoop cluster. You're going to learn how you can use Yarn to do that better. And then you're going to learn about an open source framework called Weave, which makes it easier to use Yarn. So I'm going to start with something that we all know, simple web application. Typically, I will separate my presentation and my business logic layer. So I'm just running on 2 nodes, and they somehow talk to a database. If I want to make that scalable, I can just add as many copies of that as I want, because they're all stateless. So now this is already running in a cluster. And we're all familiar with that, I guess. Now, if I'm smart, I'm going to make my web app log, and then I can save the logs somewhere, and maybe I can do something with the logs. So now I end up having lots of little log files. Okay, now I have log files. What do I do with my logs? My log files will tell me cookies of users, what they viewed, what they clicked. Maybe I can find out how long they stayed on a page, what they clicked on most often. So I could actually analyze my logs and make my web app better. I could optimize the application for the user behavior that I observe. I could actually personalize the experience for every user. But a lot of people don't do that. And why is that? Well, now you have these web logs. They are huge. They're gigabytes, sometimes terabytes of data. And how can I analyze them? How can I even store them? It's so much data, it's really expensive to store that. And do I know how to run an algorithm to run over a terabyte of data? Most people don't. So for all this heavy lifting, there's Hadoop. Hadoop, its symbol is the elephant, really does the heavy lifting when it comes to big data analysis. What is Hadoop? It's an open source framework, and it's free. And by the way, it's written entirely in Java, almost entirely. And it runs on commodity hardware. So it really runs on cheap hardware. You don't have to buy an Oracle rack or a very expensive storage that is super reliable. You can run it on cheap hardware. And that makes it relatively cheap to store the data. And you can actually store a long history of your data, months, if not years of your web logs there. And then the way you analyze data in Hadoop is using the MapReduce paradigm. The MapReduce paradigm was introduced by Google in a paper almost 10 years ago. And just a few years later, an open source project started to implement that in Java, and that's Hadoop. What it does batch processing of very large files in a distributed file system. And the paradigm is very, very simple, but it's very powerful too. So Google, when they introduced this, they said they were running, for instance, their anchor text algorithm and their PageRank algorithm in MapReduce. And those are the 2 keys to their initial success, how they made web search better. And a lot of people found that you can do almost anything with MapReduce. So what do you do with that? Now you can turn your web app into a data-driven app. What does a MapReduce app look like? It consists of 2, it runs in a cluster, and it runs tasks there. And there's 2 types of tasks. One type is the mappers. Mappers read a part of the input data, and each of these parts is called a split. And then each mapper does some processing on that data and spits out key value pairs. These key value pairs are sorted, and that's called the shuffle phase, and then sent to a reducer in such a way that all the output for a single key will go to the same reducer. And now that reducer receives the bag of all those outputs for this key and can now aggregate analyze, do whatever it wants to do, and write the final output. And that, again, because the reducers run in many tasks, writes lots of parts. So these are part files. And if you want, you can then run another MapReduce job that, for instance, reads the parts that this one wrote as their input, and so on. And you can build complex workflows of MapReduce jobs, and you can run many of them at the same time in a shared cluster. And that's what a MapReduce cluster looks like. You have all these different jobs running, but there's always some nodes that are not used. Because, I mean, who gets 100% utilization out of his hardware? So when I look at that, well, I've paid for this cluster. Maybe it runs in Amazon. I'm paying, and these nodes are idle. What can I do with them? Maybe I want to run something more than MapReduce. Maybe I want to do some real-time analysis. I can't do that with MapReduce, but I might be able to do that with something else, maybe with Storm or some other real-time streaming engine. Or maybe I want to run a message passing algorithm over this data. There's actually a paper that shows that you can compute PageRank in real time using message passing. And with that, your PageRank would be available instantly whenever you see a new page. And you don't have to wait for a long batch job to finish. So in general, what can I do with my cluster if I have capacity there that I don't need right now? Can I utilize these idle resources? Well, let's look at some of the apps that I want to run. So a message passing app is also a distributed application. It runs in a cluster. It runs several agents. Every agent has some state. Altogether, the states of the agents make up the state of the application. And then they just send messages to each other and manipulate their state based on that. And eventually, either the state converges, or sometimes it just keeps running forever. But this is a pretty common pattern for a distributed application. Another kind of application is a streaming app. In a streaming application, we have actually real-time events. They come into the system, and they're processed in a pipeline of steps. And the pipeline can branch, actually, but it also runs in a distributed mode, and it can scale. Each of these little boxes here could actually have many instances. Or I could do something really simple. I've developed a web app, and I just want to test it, whether it holds up to the load that I'm going to get on Thanksgiving. And so I'm going to run a distributed load test. Very simple. I just start n nodes, and they all do the same thing. They just hammer that web service. That should be really easy to do, right? If I have spare compute resources, I'd really like to do that easily. So why am I telling you about this? I work at a company called Continuuity, and what we do is we build a big data platform that allows you to run all these different kinds of things in a single cluster, and it makes it really easy. So right now we're running things like real-time stream processing, ad hoc queries, MapReduce jobs, and several other things in a Hadoop cluster. Which means for us, this is really a big problem, and we need to solve this. We need to find a good way to do this. And what we really want is a multi-purpose cluster, where all these applications, all these different types of applications, can run at the same time, coexist with each other. And how do we get that? We get that with Yarn. So what is Yarn? For that, I have to go a little bit into the history of Hadoop. So when Hadoop was written, it was written solely as a MapReduce engine. And because it runs on a cluster, it had a cluster management component. But that was tightly coupled with the MapReduce programming paradigm. So the only thing you could run was really a MapReduce job. And in the latest version of Hadoop 2.0, that has been changed. So now the resource management of the cluster has been decoupled from the application management that actually understands the programming paradigm that I'm running. And the good thing about that is now I can run different types of applications in a Hadoop cluster. Yarn, just like Hadoop, is written all in Java. It's multi-tenant. It has security. And so you can actually run, if you have clients, you can actually run different clients' jobs in the cluster, and they cannot impact each other. It scales to many thousands of nodes. Most people don't have a need for thousands of nodes. Most people who run Hadoop run a dozen nodes, and maybe after a year they go up to 100 nodes, but few people go to 1,000 nodes. There's companies, however, like Google, Yahoo, Facebook, Twitter. They run clusters of thousands of nodes because they really have extremely big data. And Yarn works on a 12-node cluster equally well as it works on a 5,000-node cluster. So if you have a growing business, you can start with a small cluster and you can grow it, and eventually you reach that scale where you really need something like Yarn. Yeah, what does Yarn mean? I believe it means yet another resource nanny or manager. It's not clear. The way it works is that it adds one machine to the cluster, which is the Yarn resource manager. And the resource manager knows about all the resources in the cluster. And then every application needs to add one node to its application, which is the application master. And the application master communicates with the resource manager to obtain resources from the cluster. Once it gets these resources, it can start tasks and is now able to control the application. So how does it work? Every node in the machine, of course, it has memory and it has CPUs, but Yarn takes a slightly more simplified approach to it. It simply says every one of these compute machines has a number of slots. And a slot is, you can say, is a container in which I can run a task. And on each machine, it runs a process, and that process manages and monitors the slots of that machine. A slot is really a JVM. You can run any Java job there. You can actually run any shell command there if you want. What the resource manager does is it assigns slots in the cluster to an application. The application has a master, and the master requests slots. Once it has the slots, it can start tasks there and is now in control until it releases those slots. Okay, a few more details on how this works. So anything that's pink here belongs to Yarn. There are 4 protocols involved. The first one is I have a client. This can be my laptop. And from this client, I want to submit an application. And the first thing I have to do is I have to start the application master. For that, I use the client resource manager protocol. Once the master is running, it communicates with the resource manager to get resources. That's the resource manager. That's the application manager resource manager protocol. There's also a node manager running on every node. In order to start a job in a slot, the application master can't do that itself. It needs to submit a request to the node manager. The node manager does it on behalf of the application manager. So this is how it works. Looks fairly simple. Or does it look complex? I don't know. Simple? Complex? Simple. Wow. Okay, you think this is simple. Good. Have you written a Yarn application? So I thought this is simple when I started using it. Okay, so let's go a little bit more into the details. How does it actually work? And let's just look at the first step. The first step is to deploy or to actually start the application manager in one of the slots in the cluster. That's the first thing I have to do. So let's see how that works. I have to give you a little bit of background for that. So let's not forget, this all runs in a Hadoop cluster. And Hadoop has a distributed file system, which is called HDFS. All the data that jobs in the cluster can share are in this distributed file system. And the way it works is that every node has a local file system, and it contributes a part of its local file system to this distributed file system. Now, when I run a job locally on a node, it sees only the local file system through the native file system protocols. Java file, Java I/O, right? If I want to see things that are on the distributed file system, then I need to go through the HDFS protocol. I have to use a different file system protocol, file system client. So an important implication here is that when I run a Java job, this Java job, this JVM, can only depend on files that are in the local file system. It cannot depend on jobs that are in HDFS because the JVM doesn't understand HDFS. And so what does that mean for us? We want to start an application master in the cluster, and the client has the jar file with all the classes on his local file system. Now, if we would just say, okay, Yarn, start this class. This is the main class started in one of the nodes. That slot in the cluster cannot access the local file system of the client. So in some way, we have to copy the jar file into the local file system of that compute slot, right, of that container. And the way we do this is before we submit the job, the client uses the HDFS protocol to copy it to the distributed file system. It then sends a request to the resource manager and points it to the location on HDFS. The resource manager tells the node manager, I want to start this job. And the node manager copies the jar file from the distributed file system into the local file system. And now we can run a JVM that loads the classes from there. So it's a little bit more complicated than one would expect at first. So what does that mean when I'm writing a Yarn client? What are the steps I have to follow? So just for this first step to start the application master, I have to first connect to the resource manager. Oh, the step 0 is copy the jar file to HDFS. So here I'm assuming that it's already there. I connect to the resource manager, then I request a new application ID. From now on, when I talk to the resource manager about this application, I have to use that ID. Then I create a submission context that identifies the application. And I create a container launch context that describes the container, the requirements for the container in which I want to run the master. Then I can define, in that context, I can define the local resources. What are the jar files and other resources it needs that have to be copied to the local file system? I can define what should be the environment, any environment variables I want to set. Then I have to define the command, and the command is actually a shell command. And then I give it resource limits. I can say this particular container can only use 2 GB of memory. If it goes above that, kill it. And so once I've done that, I can submit the request to start the application master. Okay, so I can take you through the code. I have probably 8 slides that explain exactly these 8 steps. Who wants to see the code? Oh, really? That's interesting. Okay. Let's see if we have enough time to do this. What I have to do first, I have to get a Yarn configuration object. That extends from Hadoop configuration. I have to get the actual location of the resource manager, its IP address and port, from that configuration. And then I create a new configuration, a Hadoop configuration. In that configuration, I set here I set a security class, which is kind of awkward because I don't know what it does. It's simply something I have to do. I could say I don't want to run security, and then I can use a different class here. And then I create a protocol. In order to create a protocol, I have to go through a factory method. The RPC here is a Hadoop RPC factory. And I have to provide the class that I want to get and the configuration. So now I have a protocol. With that protocol, I can talk to the resource manager. So as I said, the first thing I have to do is I have to request an application ID. That's what I'm doing here. In order to do that, so Yarn uses protocol buffers for its serialization of objects and its RPC calls. And for that, you use a factory method to instantiate a request. So here I call records.newRecord of the getNewApplicationRequest class. And whenever I make requests in Yarn, I do this in the same way. This is the pattern. I go through this factory to get the request, and I can set properties on the request, and then I can send it. And then I construct an application context, same way. And, oh, something is missing here. We can't see the last line. So here I basically create a container launch context from two things that I just generated. Don't know what happened here, why this doesn't fit on the screen anymore. Okay. So now I have the context. Now in the context, I have to define the local resources. And basically what I do is I have to set for every jar file that I want to have copied to the local file system of the application master's container. I have to describe that. Where is it on HDFS? What type of file is it? Is it just a file, or maybe it's a zip file that has to be expanded, or is it a directory that has to be copied? I have to say what is the actual path on HDFS. I have to give the modification time and the size of the file. And the reason for that is after it gets copied, this is used to verify that the file is actually the same, that it hasn't changed in the meantime, or that it hasn't been corrupted when it got copied. And I put that into the local resources, and I can do that for as many jar files as I need. I can do that for property files. I can do that for whatever resources I want in the local working directory of that container. Then I define the environment. That's simply a map from string to string. Important thing here is if I want to have a class path set, I have to define that. The framework doesn't do that for me. So if I copied any jars into the working directory and I want them to be available to the JVM, I have to add that working directory to the class path. I guess for security reasons, it's not there by default. And then I define the commands. So what am I going to run? I'm going to run a Java command, a JVM. I'm going to run the main class myAppMaster, and then I run some arguments. This is where you would fill in whatever your app master does, right? And whatever arguments it takes. And so I add this command to the container context. I define resource limits in the same way again. New record, set some properties, and add it to the context. And then finally, I can submit the request. So now that it's submitted, I'm pretty much done. Because this happens once the request is sent, and it is sent successfully, everything happens asynchronously. I don't need to wait for a response. The response will always be OK. I can go back later to the resource manager and ask about the status. But here, I'm pretty much done in the client. OK, do you still think it's simple? Sure, OK. All right, so now I'm in a state, I have started the application master. I still haven't started any tasks, right? It's now in the cluster, and there is a resource manager. So what do I have to do? I pretty much have to repeat. Now in the application master code, I have to repeat all these steps that we just did for every task that I want to run. And I do that in a loop. So the first thing the master does, it registers itself with the resource manager. It says, hey, I'm here. I was successfully started. And then it goes into a loop. This loop should probably run maybe every second and send a request to the resource manager. This protocol to the resource manager is a single API call. And this single API call has, as we see, 5 purposes. So the first purpose is the application master sends its heartbeat. It says, I'm still alive. Second thing is it can request containers. It can say, give me 5 more containers with this much memory, and so on. It can also release containers that it has previously received. So it submits that, and then now it receives a response from the resource manager. That response may or may not have some containers. It probably will have some containers because we requested some. And it'll also have a list of containers that have previously run, but that have just terminated. So when they have terminated, I know I can release that container. So now I have received some containers from the resource manager. Now I want to start tasks. And in order to do that, I send a request to the node manager. And that request looks very, very similar to what we just did in the client to start the application master. Right? And I send that to the node manager and say, please run this task for me. And the node manager does all that for me. Couple of caveats here. So the rule is an application terminates, and after all the tasks have terminated, the application master can terminate. If the master terminates first, then the resource manager doesn't know what to do with the tasks that are running. They are now zombies or orphans. And because the resource manager doesn't want to waste resources, it's simply going to kill them all. So you better write your master in a way that it doesn't crash. There's some plan to support restarting of the master in case it crashes. The problem with this is that the master has some state, right? It knows about all the nodes that it has, all the slots that it has, all the jobs that are running there. It maybe knows the state of each of them. And now if it crashes, it loses all this state, right? So when you bring up a new application master, it doesn't have that context. So that's the question, what's the point? So this would only work if the application master had a way to persist its state, and that's not there right now. Also, so starting a task in a container is very similar, as I said, to starting the application master. It's always the node manager that runs on a particular compute node that manages a slot. That node manager will start the process for you. And the node manager will then also monitor it. If it crashes, if it fails, it will notify you. But it can't notify you because it's not talking to you, right? What the node manager does, it informs the resource manager and says, here's a failed slot. And then the resource manager, next time I call it, it's going to respond to me, oh, these slots have terminated, either crashed or with normal conditions. And then when I find out about that, just because the slot has terminated, it's still mine. Because I may have data there. I may have logs there, whatever, that I want to collect. So the resource manager is not simply going to claim it back from me. I have to release it explicitly. Another tricky thing is how the interaction with the resource manager works. It's completely asynchronous. So when I send a request and I say, please give me 5 nodes, or give me 5 slots, most likely the response will contain 0 slots. Because all that this request does is registers that request somewhere in the resource manager, and now the resource manager will fulfill my request asynchronously. Next time I make a call, I'm probably going to get back some slots that are requested in the previous call. So if I don't get back any slots, that doesn't mean that the resource manager didn't understand me. It just means it may take a little while. If I make the same request again and I ask for 5 again because I didn't get anything back, that adds to the 5 that I already have. So now I have requested 10. Right? So every call to the resource manager, every request is incremental. And the master itself needs to keep track of what it has requested, what it has received, and how much more it needs. Another interesting thing here is when I run a distributed application, I probably want to have application logs. When something goes wrong, I want to look at the logs. Right? The way that Yarn does this, and this again has to do with the distributed nature of the file system. Every JVM will log to the local file system. When the job has terminated, then those logs get copied into the distributed file system. And then the client can retrieve them from there. Now, that's a little bit difficult if you have a job that never terminates, that runs forever. But OK, that's on a different sheet of paper. But this is the way that you can retrieve logs. OK, I was going to show you an example until I realized how many lines of code it is. The simplest example that you can write would be an application that takes a shell command and runs it in n containers. Nothing but that. runs the shell command, and then terminates. This is a sample application that comes with Yarn when you download the code. And it's 1,681 lines of code for a simple Hello World example. Over time, the APIs have improved a little, and it's got a little bit simpler, but it's still, in the current version, it's like 1,500 lines of code. And the conclusion that I draw from this is Yarn is not simple at all. And my colleague Terence is going to step up now and show you how it can be made easier.
So, as you've seen, Yarn is powerful, but at the same time, could be pretty complex to write even a fairly simple application. So there are several shortcomings about Yarn. So first of all, you see the complexity. The protocol itself is relatively complex. The API itself is very low level, very robust. So you have to write out everything that you want, right, through the API that it provides. And also, the clients need to actually interact with the HDFS. They need to set up the environment. So you need to know about how the Hadoop environment is being set up, everything. So basically, it's like you have to do everything manually by yourself, right? And also, the other things that Andreas mentioned is that the log collections won't happen before the application actually terminates. That creates a problem, especially for us. For example, if you're running a real-time analytics programs, right? It never terminates, right? Because the real-time streams keep coming in. So you never be able to see the logs. And if there's something happen, you never be able to know, right? And also the application master, as of the current version, is a single point of failure in Yarn because it doesn't support restarting an application master. And then between the application master and the containers that you start to run the task, there is no defined communications. So basically, you're on your own. If you want your container to communicate with your application master for status, for messaging, for any kind of thing, you have to work out your own protocol to do that. And all this make it really, really difficult to debug. That's what we draw from my experience when we start to use Yarn. And we think that most of the typical distributed applications are relatively simple, simple in the way that you always want, I have a bunch of tasks. They may be the same task, they may be different tasks. And then I want to run it on a cluster with n number of instances of this, n number of tasks. So there are several examples, right? For example, I want to run m procedures and m consumers for a limited amount of time. Or actually the tasks that I write, I don't want them to be aware of the Yarn, right? Because if I write my task in a way that it has to be aware of the Yarn, it makes it really difficult to write, for example, unit tests or small-scale tests or integration tests, because you always need a full-scale Yarn cluster to run your task, right? Which is not desirable in most of the scenario. So that's why we think, can we actually make writing application on Yarn as simple as writing Java threads? I believe most of you actually deal with Java threads, right? Right. So you simply just, how to do it, right? You simply implement the runnable interface or the callables, or you extend from threads, right? A couple of ways. And then you start the thread, or you submit your runnable to an executor service, right? So, and what beyond that is for a distributed application, it typically needs several more supports from the framework itself. For example, monitoring and restarting of the containers. Like, for example, if your task kind of get killed or die, or exceptions and it exit itself, you might want to have logic to restart the task so that it can keep on processing incoming data. And you want to have like more close to real-time log collections and metrics collections, rather than you have to wait for your application to terminate in order to do that. And also you want to have an elastic scaling, which means you can say, let's say you are using Yarn to run a bunch of application servers. Okay? So you want to increase or decrease the number of instances based on the current load. And you want to do it dynamically. You don't want to stop your applications and then reconfigure and restart it. You want to do it in real time, right? And of course, for long-running jobs, for real-time jobs and other type of services as well. And that's come the Weave. So Weave, what is Weave? So Weave is a library that we built that can complement Yarn to make it simpler, much simpler to use. It's an open source project. It's an Apache 2 license. It's hosted on GitHub. So what it provides several things. First of all, it provides a generic application master, which means you only need to focus on the task. An analogy would be you only need to focus on writing your runnable. You don't have to worry about like how to run it, how to negotiate with Yarn, or things like that. And the Weave library provides a DSL for specifying how your applications should run, like how many tasks it contains, how many instances, how many resources, things like that in a very, very simple way. And then provide a set of API for you to use to define your container task. Basically, I'll show you later, but basically we call it Weave Runnable, which actually is extend from Runnable itself, so that you can simply write your task by implementing the run method and also the init and stuff, like kind of lifecycle methods. And also it has built-in support for service discovery, logging, metrics, and monitoring as well. You might not see the details of the code, but just to showcase, if we use the Weave library to write this distributed shell applications as being the example application that you can find in the Yarn distribution, if you just look at the important part of the code, so if you remove all the boilerplates, the Yarn version takes around like 500 lines, okay? And then the complete program that you write in Weave, it takes around 50 lines. So that's the simplifications that we are talking about by using Weave to write distributed applications that can run on a Yarn cluster. So this is how the framework looks like. So the yellow part, the Weave client, is the thing that you use and you interact with. Basically, it's a set of Java APIs that you can use. All you need to do is to define a bunch of Weave runnables, right? And then you submit the application through the Weave runner, which is similar to an executor or executor service. And then the Weave runner will do the rest for you. So it talks to the Yarn resource manager, and then it will submit the generic application master to run, and then that one will take all the runnables and the specifications and request appropriate amount of resources from the Yarn cluster to run the runnables, to run the task that you specify and that you submit through the client. And it also uses Zookeeper. How many of you know Zookeeper? Okay, that's good. So it also uses Zookeeper. So Zookeeper, in one sentence, is basically a distributed cluster management tools. State management tools. So we use Zookeeper to manage the states and messaging between the application master and the client, and also between the application master and the task that it starts on the Yarn cluster. And one thing you might notice is in the application master that we start, we also start an embedded Kafka server. So Kafka is a very lightweight pub/sub system that which is an open source system as well, that we use so that all the tasks that we start on the Yarn cluster, for the logs and metrics, they actually will keep publishing to the Kafka system, so that it's very easy to build to consume the logs and metrics, so that you can have a real-time views on all the logs and metrics being emitted by all the tasks in real time. So this is how it looks like. So let's look into a little bit more details. So let's say now you want to write an application using the Weave library. What you have to do, so right now this application is showcasing a echo server, which is a very, very simple one. What it does is when it runs, it binds to a random port and then start reading in incoming message and then just write it back to the same client and close the connection. That's what it does. So I skipped some details about the actual server part, but I believe everyone of you will know how to write it. It's pretty simple. So to define that, you basically have your class implements the Weave runnable, which itself is actually a runnable. And then you can use the standard SLF for JLogger to write out your log message. The with framework itself will pick that up, so it will have the right appender and then start publishing the logs to the Kafka when this task starts. And then you can get something called a with context from the with runnable, so that you can interact with the runtime context. For example, knowing which host you're in, or want to interact with the discovery service that provided by the with library. And then you simply just implement what you want to implement in the run method. So it's basically no different than you implement a thread, right? And also there are some extra support, like for example, you can say context alarms, and then you can say, well, I have an echo service that are available on this host and this port. Okay, that's what the with library will provide it to you, so that when you write your client, you can actually use the discovery service to see, oh, actually I have like 10 nodes that are running this particular service, and then I can select one of them, and then start talking to it or something like this. So it's a pretty standard way of using discovery service. And that's it. So that's as simple as that. So after you write your task, right, you write your runnable. Now you want to run it, right? So how to run it? So you have something called a with runner, which is like an executor, okay? So the library will have a way for you to create. So you just say with runner, and then you new a yarn with runner, okay? Then you can say I want to prepare to run something. So you say runner.prepare new echo server. So you just new your runnable. So right, you don't say echo server.class. You just new it, okay? And then you prepare. After you prepare, you can do some more modifications to this particular run. So for example, you can attach a log handler. So this one simply just collect all the distributor logs and print it out to the console screen that you run your client. Okay, but you can do other stuff. You can have a log collectors, log handlers that actually collect the logs and write to some other file, HDFS for future analysis, or you can hook it up with the monitoring system to detect any failure or any problem with the containers that are they're running. So, and also you can do a bunch of stuff like manipulating the class path, adding some more extra resources, things like that. But let's say you just want to start it, right? So now you prepare and then you start. After you start, you get something called a with controller. A controller is simply just expose some method for you to control the running applications. So you can, for example, send some commands, which is like message, right? You define your own message. It's simply just key values things that you can send to the running applications, right? And then you can actually send to a particular runnable as well if your application is like having a lot of different tasks. And then you can, of course, stop the application. There are other methods that are available in the controller. For example, you can attach listener so that you know the changes of the state, running state of the application as well. Those are kind of for advanced usage. But you can see it's as simple as that. So with these two slides, you already be able to start applications that runs on a Yarn cluster, which makes your application a distributed applications already. So I would like to go a little bit deeper. So for example, you have more than one task. So that in that case, we call it an application. So application basically is a collection of runnables or collection of tasks. And the application will provide a specification. We call it with specification, which you basically specify like what are all the runnables. And for each of the runnables, you can say, I have a bunch of files and resources that I wanted to be available locally. And then you can also say, for this particular class task, I want to have like 5 instances of them, which each of them will have 2 cores and like 2 gig of memory, something like that. You can, using this DSL to specify things that constitute the whole applications. And the with API also supports something like, well, you can define a bunch of tasks, and then you can define like the ordering, like the starting sequence of them. So for example, if your applications have multiple things that you need them to start in particular order, you can say that as well. And so you construct your applications, and then to start it, it's more or less the same way. You basically use the with runner, and then say prepare. Now you prepare the application, not a single runnable. You prepare the application, and then you say start. Exactly the same way like the previous slide. And as I mentioned, you can also specify order, like for example, if your application have 3 things, like input reader and then some processor and then output writer, You want to start the reader first, and then the processor, and then the writer. So you can specify it like this as well. So in summary, most of the time we see people like having applications that generate a lot of data. Hadoop itself, the MapReduce programming paradigm, is kind of designed for processing a large amount of data. But in terms of like batch processing a large amount of data, that's what it is good for. That's what it is designed for. And eventually, the Hadoop ecosystem, kind of evolved, and they also recognize that the Hadoop cluster itself has more potential than just running batch jobs, right? So that's why they build a Hadoop 2 and then try to separate out the resource manager and the Hadoop and the MapReduce programming itself, so that you can starting to use Yarn to write different kinds of application beyond MapReduce. And then we try to use that and leverage that power. And eventually, we designed it with, which we believe makes Yarn much easier to use. And as the previous keynote, some of you noticed, easy to use is the key to success. That's what we believe as well. And we believe now we can turn like any Java developers to be developers that is able to write distributed applications that can run on a cluster that can scale from like dozens of nodes to thousands of nodes in the same way. Thank you. So that's, I think it's question time, right? So there are a couple of links here. The first one is the GitHub link of the Weave library. So anyone interested, you can check it out. The second link is the link to the Hadoop Yarn, is the official site of the Hadoop Yarn distributions. And lastly, we have a company called Continuuity, and we are hiring.
Okay, that's it. Thank you.